Of all the techniques for solving differential equations, separation of variables is probably one of the quickest. It doesn't work on every differential equation, but it works on differential equations that are of this particular form. So the slope of the unknown function y is a product of two separate functions, one that depends only on x, one that depends only on y. The way that you solve it is like the following. You move that 1 over gy, move the gy over to the other side, and then what you do is you say, well, I've got a derivative, I need to find an antiderivative. So what you want to do is you want to write an antiderivative. So let's integrate both sides with respect to x, because both of them are actually functions of x. You say, wait, this is a function of x? Oh yes, yes it is. Why? Because this y is a function of x, and this is y prime, which is a function of x. Okay, yeah, so I can integrate both with respect to x. Okay, so proceeding, you will notice that in essence the left side of this expression, this guy here, probably involves a substitution. But one way or another, you can evaluate it, and this guy here just integrate outright, or anti-differentiate outright. And don't forget the plus c. You don't need two plus c's, because you don't know what the constant of integration on the left is, you don't know what the constant of integration on the right is, so you might as well just use one. So constant of integration is only on one side. If you understand this, you understand separation of variables. Okay, so let's take a stab at it. Let me give you an example. Okay, this is a differential equation. I solve it by separation of variables. So move the y over to the other side, integrate both sides with respect to x. The right side's no problem. The left side, what about that? Y prime over y. Where have I heard that before? Yes, y prime over y is natural log of y. Okay, cool. So this is natural log of absolute value of y. Great. I want to solve for y. What do I do? Well, let's exponentiate both sides. So I get absolute value of y is equal to e to the 1/3 x cubed plus c. I could split my exponents. Let's split my exponents. And e to the c, I don't know what c is. So I also don't know what e to the c is either. So I might as well just replace that with some random other letter. I'll call it a. And that is my solution. In fact, I could get rid of the absolute value bars because that just means I need to choose my a carefully. So this a is an arbitrary real number. Anything like that will be a solution. Okay, cool. If I had an initial value problem, so I knew what the value of y is for some particular x, then I could write down an equation for a and figure out what that a had to be. No problem at all. So that's pretty much how you do separation of variables. It's worth noting, though, that sometimes it's useful to have a few extra algebraic tricks in your back pocket, because sometimes they turn out to be really useful. So let me give you one other example of that. This is a differential equation that has two equilibrium solutions. They are y is equal to 1 and y is equal to negative 1. If I put in 1 or negative 1 for y, remember these are functions of x, if I were to put them in, I would get 0 for y prime, and that means that the solution is constant. Okay, all right, so given that particular observation, let us proceed. And what are we going to do? Well, we're going to write something like y prime over 1 minus y, 1 plus y, equals 1. Okay, anti-differentiate both sides. Oftentimes people like to write this as dy because they're really doing a substitution outright. That's okay. Just don't forget to put the x back in when you're done. All right, so that's the left side, or rather the right side. The left side presents a little bit of a trouble. How do I evaluate that integral? Well, remember your algebra. And there is a trick called partial fractions. Partial fraction says, I'm going to try to rewrite this product like this. If you do this, I can multiply both sides by that common denominator. Let's multiply both sides by that common denominator to clear out all the fractions. The left side just becomes 1. The right side, one of those factors cancels out in each case, and I'm just left with this. Okay, let me regroup a little bit. Let me regroup a little bit, and you will realize that I've got something like this. Now, an observation here is this must hold, not just for one y, but for all y. So if that's the case, the only way I can get this to happen is if these two separate equations hold. This last one here, this one here is what comes from that term there. Okay, now I can say that a has to equal b, and that means that a equals b equals 1/2. Okay, so after all of that wrangling, I now know that if I try to compute this antiderivative, I could write it as this sum of two antiderivatives. And the nice thing about that is I know what these two guys are. This is 1/2 natural log 1 minus y. This is 1/2 natural log 1 plus y. Okay, now going back up to the beginning here, this line, that should equal x plus c. A little bit of rearranging suggests that I should write this natural log as a fraction, or rather as a product. Oops, I realize I did the substitution wrong. This one's supposed to have a minus. Okay, and this is our final solution, this equation here. One thing you can notice right off is that if I put in y equals -1, I get natural log of 0. That's a damn shame, but I know what the solution is. Same deal with y is equal to 1. But everything else works perfectly fine. So the point is that since we knew what our equilibrium solutions were from the outset, this solution just works. Of course, you can go ahead and solve this for y if you care to. You will find that there's 3 different classes of solutions. How do I know that? Well, just refer back to the slope field. The slope field for this differential equation looks a bit like this. I've got my 2 equilibrium solutions, one at 1 and one at -1. And if I put in y equals 0, you will notice that the y prime is positive. That means that my slopes are going up. If I put a number for y that is like 2, I'll get 1 minus 2, that's a negative number, times 1 plus 2, a positive number. That means the slope is decreasing. If I put in a number like negative 2, 1 minus negative 2, negative 2 plus, 1 minus 2, I'll get a 3 times negative 1. That's a negative number as well, okay? And so my slope field looks a bit like this. So the typical solutions are those two equilibrium solutions, as well as the following. A solution that comes like this, a solution that goes like that, and one heterocline that goes from one to the other. And so you can kind of see the reflection of that behavior in the presence of the absolute values. So by choosing all the different possible cases you need to choose for those absolute value signs, you'll pick up all those three different classes of solutions, and the equilibrium solutions break the natural log. So those are the other class of solutions. So in a nutshell, this is how you do separation of variables. It only works when your differential equation is of the correct form. Choose the wrong form, it won't work. But if it's of this form here, you can move all the stuff on one side to be x's, all the other stuff to be y's, integrate both sides, and collect up the pieces, solve for y.